All right, folks. This is the first of three videos about binary search trees. Binary search trees are maybe the first truly interesting data structure that people come across. Lists are surely the most important. Binary trees are also a very important data structure. Binary search trees are when we start to see that the choice of data structure you make and the set of invariants you apply to that data structure to make sure that it's correct are hugely important and can make or break the difference between efficient and inefficient code. But choosing the right data structures is so important. Now, we have a whole course after CS54 that talks about this. We're not going to actually talk about efficiency. We'll get some intuition for it, but we're not at all going to talk about it in this course. Even so, I want to introduce you to some of these data structures. One, because we can express them very cleanly in Galena, and two, because it's nice to see things more than once. Okay, let's get started. So binary search trees refine binary trees. So what do I mean by that? Well, they establish an invariant called the search property. There's a lot to unpack there. So refining a data type means you're going to say, oh yes, I look like this data type. I have the same structure as binary trees, but I only want to talk about some subset of them. So for example, you might think back to the binary numbers where like the function normalize takes arbitrary binary numbers to sort of canonical or normal ones that don't have that weird leading zero problem that all of the other binary numbers did. Um, it is just a coincidence that binary is in both of these names. It's because they both have to do with the number 2, nothing to do with invariance. Okay, so an invariant, literally that word means something that doesn't change. In the computational sense, it means a thing that should always be true, is the sense in which people use it. So binary search trees are binary trees that respect a particular invariant, that satisfy this invariant, right? That have some property all of the time. This property is called the search property. That's what makes them binary search trees and not just binary trees. Okay, I'm going to tell you the version of the search property that we'll be using in this course. There are some variations on it. If you go to Wikipedia, they'll give a slightly different search property. A binary tree T is said to have the search property when for a given ordering, that is to say some notion of less than or greater than, we're just going to talk about nats here, uh, either one of these two bullets holds. Either T is empty, okay? The empty tree has the search property, just by fiat. And it's a rule I'm going to give you. Or T is a node, where, now I'm going to give you some conditions. Okay, the children L and R also have to have the search property. And they could have that by fulfilling either of these two branches. L and R could both be empty, one could be empty, the other maybe not. But whatever shaped binary tree they are, they have to satisfy the search property. Okay, there's two other things, and this is where the search bit comes in. Every value in L is strictly less than the value at our node. So if we're at some tree, and we have a node here, then everything on the left, if I'm mirroring correctly, everything here should be less than our node. Right? And then similarly for the next bullet, everything in here, everything in R, should be strictly greater than our node. Everything in here should be greater. Okay. This is the search property. It turns out this is a really, really useful property. So we'll see this more in the next video, but suppose you have a binary search tree and you wonder if some value n is in it. First, you look at the root. If that's it, great, you're done. You don't have to do anything else. Otherwise, you just ask, hey, is the number I'm looking for, is it less than or greater than this thing at the root? If it's less than, then you only have to look in this part of the tree. Half the tree down here, you don't even have to consider at all. If it's greater than, then you look in here and you ignore the less than part. If your tree is sort of well balanced, if about half is on either side, you'll do almost no traversal at all. If you kept a list and you were looking for n, you could have to look almost arbitrarily far down that list to find the number you were looking for, or object or whatever. So binary search trees mean that you can do less searching, right? It's called the search property because it helps you search. So it turns out also that not only is looking things up, searching for things in a binary search tree really efficient, so are other operations, adding and removing elements and things like that. So in this file, you're going to implement a few. Um, there's a caveat here that talks about other versions of the search property that people might care about. We're doing the one where it's strictly less than, strictly greater than. It ends up being a little more useful for what we're going to do on day 8. Okay, so to start with, I want us to just explore, this is going to be the rest of this video. I'll make other videos for the rest of the binary search tree stuff. To start with, I want to explore what is the search property? What counts? So you have homework here that asks me to define for you a couple of binary search trees and a couple of non-binary search trees, things that don't satisfy the problem. Okay, so to do this, you're going to have to look closely up here and sort of think to yourself, what counts as having this property or not? So I'm actually going to sort of do some of this for you right now, with you right now. Let's define a binary search tree. Definition, my BST. It's a BT of nat. So we're only going to talk about trees of naturals because it's the only thing we have a notion of ordering on, right? We've defined LTB, LEB, and all that. So we'll do it. We'll do it there. Okay, so here's a binary search tree. So I'm going to do a binary search tree with 3 values in it. Ooh, I love the idea of batnat. Like, quick to the bat natural. No, BTNat. Okay, so let's check my BST, right? So we saw the type. Let's print my BST. So it looks something like this. So I used this leaf thing, which is the same thing as node, empty, whatever. So let's see whether or not this has the search property. So let me scroll up. Here's our search property. So my BST is a node, which means we're going to be in this case. So it needs to be the case that this has the search property and this has the search property. Now I want to make an observation. Then we'll go back to my BST. Every leaf has the search property. Why is that? Let's think about it. Well, a leaf has the form node empty v empty for some value v. Okay, what's going to make that leaf have a search property? Well, L and R have to have the search property, but they're both empty, and we know the empty tree has the search property. So check, this one's easy for leaves. Every value in the left-hand child is less than v. Well, there's no values, it's a leaf, right? The left child is empty. So check. And then every value in R is greater than v. Again, there's no values in R if it's a leaf. So check. It's a binary search tree. It has the search property. So both leaf 5 and leaf 20 independently have the search property. Great. Okay, well, now we have to ask about this upper node, though. So node, we just established that L and R have the search property because they're leaves, right? And we know that they're going to have it. Is everything in L less than the value V? Well, yeah, there's only one value in L, 5. And 5 is less than 10, strictly. Every value in R, is that greater than V? Well, here's R. R is just the leaf 20. Yeah, it is. 20 is greater than 10, and it's the only value there. So that's a nice example of something that's a BST. Let's look at something that isn't. Oh, funny keyboard alignment. Okay, so let's check this one. What gets violated here? Now it turns out more than one thing's going to be violated. So what makes this not a binary search tree? Well, so we're in this case, so then one of these has to be wrong. Okay, these parts are fine because the left and right child here are both leaves. So we already established that all leaves have the search property, so we're fine there. Every value in L is less than what's in V. No. No, no, no. Here's our left child, and it's greater than what's in 1. What's in V? What 1? 3 is greater than 1, is what I'm trying to say. So no, we violated the second point of the search property. Let's look at the right-hand child. Oh, we have a problem here too. We need every value in R to be greater than V. Strictly greater. Not greater than or equal to, strictly greater. And 1 is equal to 1, not greater than 1. So we violated both of these second points. Okay. Now for your BSTs and non-BSTs, please don't just do R's, right? Mix it up. There are other ways to have non-BSTs. I think that we're not going to, I think, particularly check for this. You just need right answers here. But I think it would be good for your understanding. Can you find different ways of violating the search property? So I've shown you some trees that violate this. What would a tree that violated this one look like? Think about that for a bit. Okay, great. So that's it for this video. In the next video, I'm going to talk a little bit more about some operations. We're going to start by looking at the lookup, and then after that, I'll go over all of the homework we want you to do having to do with BSTs. Okay. Good luck, y'all.